welcome to everybody. And it's so great to see everybody here. I'm David Turner. I'm one of the co-conveners of the seminar. And tonight we've got Georgina Lockton, who's going to talk to us about self-driving cars in the 1960s. But before that, I'll introduce Georgina formally in a second. I just want to flag our next seminar, which is on the 11th of February, and it's Luke Sieber, and he will be talking to us about air-mindedness. Sorry, I've got the full title here. From this new culture of the air, we finally see ground-mindedness in the 1930s. So I got that slightly wrong. Thank you, Charlotte, for putting the link is in the discussion if you want to book, and you can book right now. It's open to booking. So tonight, as I said, we got Georgina Lockton, who is a final year doctoral student at the Centre for Urban History at the University of Leicester. Her Arts and Humanities Research Council funding PhD is on research into road safety in the 1960s in Britain, and is conducted in collaboration with the Science Museum. In 2020, she held an internship at the Department of Transport, where she wrote a report on current policy and practice in road policing. And as I say, tonight she'll be talking about cars in the self-driving cars in the 1960s. So Georgina, over to you.
Thanks, David. I'm just going to share my PowerPoint, hopefully. Do you have the PowerPoint?
Yes.
Lovely, thank you. Well, thanks for that introduction. So this evening, I'm going to speak about vehicle automation as a proposed solution to the road safety problem in 1960s Britain. And I'm going to do that by providing an object-centered analysis of a Citroen DS19 driverless car. This car was modified by the British Road Research Laboratory, which I'll refer to as the RRL throughout the paper, throughout the 1960s. So being partly based at the Science Museum has given me unlimited access to their collections, and I took the decision to begin each area of my research by looking at different objects. Part of my brief from the museum was to investigate some of their artefacts, including to look at how they actually worked. And this has been useful for my own research, as well as for informing exhibitions at the museum. So I'll begin today with a discussion of the method I've devised for using objects in historical research. I will then uncover the modifications made to it by the RRL before going on to look at other sources. The amount of printed documentary and secondary literature about vehicle automation at this period is limited, adding to the value of using the surviving object as a historical source. I'll address the question of why automatic vehicle control was researched in Britain during the 1960s and where the origins of the design came from. I will then conclude with an overview of the use and significance of the driverless car and how it linked to ideas around road safety and congestion during this period. So using objects in historical research is uncommon. It's more popular, for example, in fields such as archaeology. History is traditionally based upon written documentary sources, so I decided to devise my own method to guide me through using museum objects relating to the history of road safety. So my research progresses through each of 5 stages as outlined in the diagram, although not necessarily in the same order. As with any fixed method, there will be objects and instances which do not fit the plan, and the expectation is that the flowchart is fluid and adaptable to change where required. The first stage poses the question of what the object is and how it worked. The second stage moves on to look at who created the item, where the idea came from, and when it was made. Rival designs are explored as part of this, along with trials of the item and any adaptations and changes that were made to it as part of the research and development phase. This lays the foundations for the third stage, which is context. For this stage, documentary and other external evidence will be drawn upon to contextualise the artefact. This section is the broadest of the 5 sections and also looks at why the item was developed at the time, pulling in evidence of wider contemporary thought on the subject relating to the item. The 4th stage moves on to explore how the item was used and whether there was any resistance to it from the authorities or the public. Finally, the 5th stage looks at the significance of the item, considering the role that it played in society at the time, as well as what the item means today. It's important to note that the stages of the model are interchangeable and have allowed for flexibility so that it can be adapted to suit a whole range of technological artefacts. The design of the model means that regardless of the order of the stages, the resulting information exposed will give a rounded picture of the item. It is also sufficiently broad that it could be applied to any artefact, not just those relating to road safety, and as such, other researchers taking an object-centred approach may find it a useful methodology to adopt with some minor adaptations to suit their particular field. So let's take a look at the DS19 driverless car as a historical artefact. On the 4th of April 1960, the Department of Scientific and Industrial Research purchased a Citroen DS19 petrol saloon car for the RRL, which the RRL was to run in a driverless mode. This was partly in response to the road safety problem, as the RRL worked to come up with solutions that would reduce road traffic collisions, as well as to minimise their effects when they did occur. So I began my research by looking at the car itself. When I first encountered the car, I found that it had dull bodywork, pitted chrome detailing and leaking fluid, which probably came from the car's complex hydraulic system, and all in the footwell of the front passenger seat. There's a juxtaposition here between the beauty and the decay of the museum artefact. The museum aims to preserve items just as they were when they acquired them, and are careful not to change them through any cleaning or maintenance process. Any cleaning or moving of the item that has taken place is carefully logged by Science Museum staff and can be read by the researcher in the records of the item. So when I first saw the car, it did not sit there with newly chromed bumpers, polished bodywork and a working engine, which would have required removing old parts and replacing them with new. Instead, it rested there in a balance of preservation and slow decay with nothing altered or changed. This enabled me, as the researcher, to see the car just as it was when the Science Museum acquired it in 1973, taking into account natural ageing that had happened to the vehicle over the last 50 years. As such, an analysis of the DS19 driverless car as it was in the 1960s, minus that visible decay, was possible by looking directly at the car itself. So on viewing the car, there are clues as to the modifications that the RRL made to the DS as part of their experimental driverless car trials. In the photo, you can see to the left of the steering wheel, a dial, which appears to be a later addition to the console, judging by its rudimentary attachment to the seamless dashboard with a metal anchorage and exposed screws. There is also a switch in the footwell beneath the steering wheel with visible wires linking up to the dial, which is clearly an RRL addition. And this is likely to have had a role to play in its automatic guidance settings. There is an unusual button in the footwell and the place where a brake pedal would conventionally be found, although this appears to be an original feature of the car. In the centre of the car is a metal panel containing 3 switches and an additional panel above it containing a 4th switch. The top switch is marked oversteer, off, understeer, indicating that this central control box is concerned with the guidance of the steering of the vehicle. Directly in front of the passenger seat, and almost rather worryingly, and mounted in the trim of the dashboard, is a simple red button as pictured, with a printed label above it which reads manual override in white capital letters on a red background. And then mounted on the near side rear passenger seat is this large metal control box containing numerous switches, dials, input and output points, which are all marked with printed labels of white lettering on a beige background. The central dial at the top of the front panel of the box is labelled differential. A dial to the left of this is labelled servo coil, and another dial to the right, servo coil 2. Labels to some of the switches below these read guidance and servo valve, indicating that this control box is a crucial element in the automatic guidance of the vehicle. Under the bonnet, the engine bay holds further clues as to the modifications that the RRL made to the DS. The front of the radiator is a complex installation of wires and metal components in the space where a spare wheel is normally found in a DS19. To the left portion of the installation is a toggle switch labelled with printed labels of white text on a beige background, which are identical to those on the box inside the car. They read fail-safe and override, which confirms that this section links with the controls in the car to facilitate that driverless mode. Having looked at the object itself, combining documentary evidence with this initial overview of the car facilitates a greater understanding of what we've just been looking at. The RRL reported that the driverless car would bring numerous benefits over human driving, most notably that driverless cars would introduce more reliability and fewer accidents, more accurate steering, allowing more traffic lanes on existing roads, shorter reaction time, reduced safe headways between vehicles and increased road capacity, stress-free high-speed travel, and cheaper and more efficient public transport. So how exactly did this work? In 1970, Mr. Cardew of the RRL produced a technical report on findings from the RRL's experiment with the DS19 as a driverless car. In it, he explained that the test car had been equipped with an experimental automatic steering system to study the feasibility of automatic vehicle control. The laboratory had buried a cable beneath the surface, which was energized with a 5 kHz current, and the car was designed so that it would follow this buried cable when running in an automatic mode. Equipment installed in the test car sensed the position of the car over the resulting magnetic field of the buried cable, and the lateral position error signal generated by this fed into an electro-hydraulic servo system. This operated the vehicle's steering, enabled the car to automatically follow the route of the energized cable. The DS19 was chosen by the RRL for modification because of the hydraulically operated components on this model. And Cardew explained the car's hydraulic power-assisted steering was an important element in choice of this car. He explained, as the command signals from the guidance system are electrical, in this case, an electro-hydraulic type of servo valve is needed to control the hydraulic system. These valves have to be supplied from a high-pressure source of filtered fluid, and this cannot be provided by many car steering systems due to the way in which they are designed. The Citroen range of cars offered the hydraulic steering system that could be used by the RRL in their automation modifications. The car had a manual gearbox and clutch, which had already been converted by Citroen to work automatically under hydraulic control as standard on the original car. This key aspect of vehicle automation, which the DS19 came with from the factory, saved the RRL the necessity of working out and installing a system which would automatically control the gear change and clutch. The hydraulic braking and hydraulic steering, which were also original features of the DS19, were easily adapted to the RRL's driverless technology. For example, the car had button-activated braking, which we observed earlier when looking at the original car, rather than a conventional pedal for mechanical braking, which meant there was no need to develop a mechanical control for this aspect of automation. And the carburetor was also hydraulically controlled as standard. The RRL therefore just needed to add a servo switch to the pipework that was controlled by their electronics. They didn't need to add hydraulics to the carburetor in order to this, as they were already there on this model. Had they chosen a different model of car without the hydraulic controls as standard, the RRL would have faced the additional task of devising mechanical controls for mechanical functions rather than being able to use servos. In this early stage of the development of their driverless car technology, the RRL's choice of an experimental car, which already had advanced hydraulics on board, gave them a perceptible head start on their work. Having taken an initial look at the DS19 before studying the documentary sources relating to it, it's now time to return to the car itself. The purpose of this is to find out whether anything further can be learned about the design and function of the car by combining some of the knowledge gained from documentary evidence with a close reading of the car as a material object. This will be achieved by asking some key questions about the automatic running of the DS19, drawing on a combination of sources. The documentary evidence revealed that the DS19 worked in a driverless mode by following a current carrying cable that was buried beneath the surface of the road. On the front of the car were two pickups, which would have detected the cable buried beneath the track. These are no longer there on the car in the Science Museum, so the use of an original photograph in conjunction with looking at the RRL report from 1970 has offered this further information. A closer look at the control box on the rear near side passenger seat shows that it was responsible for processing the signals received from the pickups on the car and worked out how much the car was bearing in position from the cable. It then sent the signal to the steering servo to steer the wheels, correcting the position of the vehicle, if it veered off course. On the back of the box, there is a manual adjustment variable resistor, which would use to realign the system over the cable if it was not centered correctly. This control box was responsible for doing the same for the accelerator. So in the space where the spare wheel would have originally been, there is a fail-safe override box, which is an RRL addition. Pipes can be observed along with hydraulic servos controlling the brakes and gearbox. Owing to the fact that these are positioned in the location where the spare wheel would have been, together with the use of an aluminium supporting framework, which is not the colour of the car's body, proves that this is an RRL addition to the car. Viewing an original unmodified DS19 confirmed my earlier suspicion that when the spare wheel is removed from the area in front of the radiator, there is a large gap left, leaving plenty of space for modifications to be added. The image shows that the hydraulic fluid accumulator, which is a pressurized fluid chamber on the left, was moved by the RRL from a space on the far right of the engine bay. This can be seen in the far lower left of the photograph with 3 hydraulic pipes connected to it. This information can only have been gathered by comparing the RRL's DS19 with an original or with a detailed study of a DS19 workshop manual. But why were the RRL researching driverless car technology in the 1960s? At their exhibition of research on roads, on traffic and safety in September 1964, the RRL proudly showcased to visitors the latest in their work to improve road safety. Held at their base in Crowthorne, Berkshire, the event lasted for 3 days and covered their main areas of research at this time. One of the areas of research which they included in the programme of events was exhibit number 28, Vehicle Guidance, where they showcased their driverless car. The inclusion of their research into vehicle guidance techniques at their traffic and safety event gives a clear indication that the RRL saw advances in this technology as a positive move towards improving road safety. Mentioned in the 1964 event pamphlet was the safety features of drivers being prevented from veering out of their lanes when driving a vehicle following an energised cable through fog. But this was just one safety feature. The RRL highlighted the benefits of automatic road vehicles in 1971, including times in increased road capacity as well as automatic observation of speed limits and safe following distances. Their idea was to introduce vehicle automation in gradual stages so that it would be widespread by the year 2000. They saw it as beginning with buses on reserved tracks, to be followed later by some cars and lorries which would be permitted to use these tracks once equipped. Following this, some motorway lanes would be equipped with guidance cables, and lorries would begin using these in groups at night, which would reduce congestion during increased road safety. It was going to increase road capacity and reduce congestion. The Ministry of Transport's 1967 publication, Cars for Cities, highlighted the official view of the possibilities of driverless cars in Britain at this period. The report, concerned with vehicle design and their use in towns, stated, "We see the main purpose of vehicle guidance in towns as being to enable vehicles to be driven safely in very narrow traffic lanes. Guidance systems might also improve safety in fog and guard against errors resulting from tiredness or inattention." The Ministry of Transport also regarded vehicle automation as a way of improving road safety, particularly on heavily used urban roads. In addition to road safety, they had their own ideas for the application of driverless vehicles in their proposed systems of overhead roads, which they envisaged would increase vehicle capacities in gridlocked urban areas. This was part of a wider literature of the period, with a focus on redesigning the urban environment to accommodate ever-increasing numbers of private cars. Safety of the automated vehicles that appealed, but also their potential for travelling safely on narrower streets to increase urban road capacity. Driverless car technology was seen in the 1960s as having the potential to enable future urban planners to approach the traffic problem in a whole new way. The modifications made to the DS19 indicate that the car was a work in progress, an experimental prototype with which the scientists at the RRL worked to develop ideas around vehicle automation and driverless car technology. But where did the idea of vehicle automation come from, particularly this idea of enabling a car to follow a current carrying cable buried under the surface of the road? In 1939, General Motors in America showed the possibilities of autonomous cars to the public in their Futurama exhibit at the New York World Fair. It was here that the idea of enabling cars to be automatically guided over powered circuits buried beneath the surface of the road was first suggested. General Motors went on to make the first cars that were designed to run in an automatic mode in the late 1950s. One such example is a Chevrolet, in which General Motors and Radio Corporation of America fitted with radio receivers and warning devices, which could operate the steering, acceleration, and braking of the vehicle. It was trialled on the roads of Lincoln, Nebraska in 1958 and followed circuits that had been buried below the surface of the road. Another example is found in General Motors' Firebird 3, which was a concept car with two engines. Steering was achieved using a central joystick control. And 1950s footage of the inside of the Firebird 3 shows that it had three buttons on the center console labeled Speed, Manual, and Auto Guide. General Motors' Auto Guide system enabled the Firebird to drive itself. It had two pickup coils beneath the front of the car, which straddled a current carrying wire that was embedded under the road surface. This idea of following a cable buried in the road is the same principle as that adopted by the RRL in their vehicle automation experiments. Slade Penora of the RRL referred to this in a 1972 conference paper, attributing the origins of work on automated vehicles to General Motors in the USA in the 1950s, shortly followed by the RRL in England in the 1960s. With this in mind, the research of the RRL into driverless car technology can be seen as having come out of an interest in vehicle automation that had begun to be explored in America a few years earlier. Scientists at the RRL who worked on the DS19 encountered a number of problems. Firstly, the steering wheel of the Citroen created a flywheel effect when the vehicle was under automatic guidance, and this caused instability. This was resolved by installing a hydraulically operated clutch to the steering column, and which automatically disconnected the steering wheel when the automatic steering of the vehicle was in operation. Cardew of the RRL drew comparisons with the driverless car technology that has so far been developed in America, commenting on how it is noteworthy in this connection that the guided cars produced by the General Motors Corporation of America, such as Firebird 3 and others, have no steering wheels at all. When steered manually, a form of joystick control is used with an electrical output to the steering servo, removing the need for a steering wheel and column assembly and its attendant problems. When under automatic guidance, the RRL's DS19 did not require a steering wheel, but a human-controlled steering mechanism of some form was, however, still required at this early stage of development, as the RRL were working on partial rather than full automation. The main fail-safe precaution taken in the experimental DS was to ensure that it could be quickly and easily returned to manual control by the driver from the automatic steering mode, if the driver felt that the automatic system was going wrong. Within this, a driver was still required to be present in the driving seat to take over manual control at any time, and thus a steering mechanism such as the steering wheel was needed to remain in place. In terms of safety, this was an important element of design. The Ministry of Transport referred to this in their 1967 publication, Cars for Cities. After considering the possibility of different types of control other than a steering wheel, they concluded that all of them involve a degree of complexity which could create new problems of reliability, and there is the additional point that universality of controls is an aid to safety. The ability of a driver to move between different cars and still be able to recognise how to operate them without vehicle-specific instruction was seen as a major contributing factor to safety. Furthermore, there was the problem of public acceptance of a system of car control in which there was no familiar manual steering mechanism. Cardew pointed this out in his RRL report, stating, to have a vehicle in which the steering wheel is disconnected from the steering mechanism as a whole may not be acceptable for cycle routes to overcome. It was for these reasons that the familiar steering wheel was retained in the RRL's DS19 driverless car. Another issue which the RRL was still yet to work on at the time of the publication of their 1970 laboratory report was that of route switching. In a system in which the guidance of the vehicle relied upon a cable buried beneath the surface of the road, there needed to be a way of making the car move from one track to another, for example at junctions or when changing lanes. Would also have to take into account merging with other traffic, whether those vehicles were under automatic control or not. The foot-operated switch mentioned earlier and shown in this photo was used in the test vehicle in conjunction with a dial indicating the position of the vehicle relative to the guidance cable, and this enabled lane changing. The RRL found in their test that this was acceptable to their drivers, but they concluded that for a wider public use, a simpler operational system would have to be developed. In the 1960s, the RRL had conducted their driverless car experiments on their test track at Crowthorne, under which they'd laid 4 kilometres of guidance cable. But in the early 1970s, they recognised the need for testing to move beyond the artificial environment of the track. In 1971, the RRL laid 16 kilometres of guidance cable underneath the near side lane of what was at the time the new M4 motorway close to Reading, taking the driverless car principle to trial in a real-world setting for the first time. This raised the issue of longitudinal control, or the braking and accelerating function, when the car was in an automatic mode. The car was able to stop and move forward on an empty road using roadside transmitters, which gave electrical command signals using the inductive communication techniques used by railways. The problem of making this technology work when other vehicles were present on the road and enabling vehicles to follow each other closely and safely remained unresolved. Public perception of driverless vehicles was another issue not easily resolved. The RRL considered that some people would not want to give up driving themselves because they enjoyed it, which would hinder public acceptance. In addition to this, the Ministry of Transport reported in 1967 on the limitations of vehicle automation if it was not perceived by the public as being able to perform better than they could themselves as drivers. successfully making a car run in a driverless mode was only the first part of the problem. In March 1972, Slade Penoira of the RRL wrote, "Civilized life requires safe, efficient transport, and there is no substitute in sight for the road vehicle. Human drivers have fundamental physical and psychological limitations which are extremely difficult to overcome, while electronic engineering continues to advance very rapidly towards cheaper and more reliable systems, with no sign that a limit is being reached. The timescale of highway automation may be arguable, therefore, but its eventual large-scale use seems virtually certain." By the start of the 1970s, the RRL were clear that the benefits of vehicle automation were twofold. In their estimation, driverless cars would facilitate reductions in road accidents of 40%. They would also ease the congestion that had been caused by too many cars on too few roads by increasing road capacity by 50%. The RRL also found that their driverless DS19 was superior to human driving on wet and snow-covered surfaces. Their tests showed that under automatic guidance, the DS maintained greater vehicle stability than when being driven by a human. They suggested the reason for this was that a driver was more likely to allow the vehicle to veer off course to a greater extent before taking corrective action. The guidance system prevented the occurrence of gross course errors and was more effective at maintaining control, as it was less likely to exceed the available tyre road adhesion, reducing the risk of accidents and human error. The conclusion of the RRL's 1970 report on the automatic steering of vehicles was that their work with the Citroen DS19 had confirmed that the guidance of a vehicle by means of a buried cable in the road and sensor coils attached to the front of the vehicle of speeds up to 80 miles an hour. While they had demonstrated this capability, they recognised that the main problems with their driverless technology lay in two areas. The first was in the quality of the ride for passengers in the vehicle, which was evidenced where the car passed over different types of road surface, which affected the pickup of the buried cable. The second was in the need to make it more acceptable to passengers. The RRL and their contemporaries in America could work as hard as possible to develop driverless car technology, but would only be successful if the government and the public were ready to accept the widespread rollout of an entire system for vehicle automation. Cost also hindered further research into the system of automation developed in the DS19 with its electro-hydraulic steering actuation system. The RRL went on to overcome this cost issue with the use of electric motors to turn the steering columns in its later driverless car experiments from the 1970s. They had also received some complaints that they'd used an expensive foreign car for their driverless experiments, which prompted the purchase of some alternative experimental cars. In a search for a cheaper, viable alternative to the Citroen, they went on to successfully apply their driverless car technology to a Mini and a Cortina in an experimental setting. This enabled them to demonstrate that electric motors made automation a cheaper model. Slade Penoira told me in a telephone interview that there was a lot of pressure on driverless research in the 1970s, as it was widely held that vehicle automation was the future of cars. But the problem of spacing between cars running in an automatic mode remained. RRL wanted to use radar sets on individual cars, which would detect electronic brake lights on the car in front and stop the car accordingly. But for the radar system to work, all cars would need to be equipped. The solution to keeping a safe distance between vehicles was not obvious when the new cars needed to fit into an existing system where other cars were not equipped with the same technology. One area where the RRL worked on applying this was with buses, which could be equipped to run in a driverless mode on reserved tracks in urban areas and thus not run the risk of encountering non-equipped vehicles. The RRL bought a Daimler Roadliner single-decker automatic transmission coach, which they converted to dual-mode control and which they successfully displayed in full running order at an open day in 1974. The bus followed the energised cable buried beneath the surface of the track and steered, stopped and started according to electronic commands programmed into the guide cable route. Despite this, research stopped because the system proved too difficult to introduce. Feedback from open days indicated that public opinion was that it was far too ambitious to roll out on open roads. In the 1970s, it was unclear how to go about introducing such a system. This, coupled with the onset of economic recession by the mid-1970s, led to government funding for the project to be withdrawn. The development of driverless vehicles at the RRL had been wound up by the end of the decade. So where does the development of driverless car technology sit within contemporary ways of thinking about road safety in the 1960s? The suggestion in the 1960s was that speed could be enjoyed safely with automatically controlled vehicles. As Cardew indicated in the RRL report on the DS19, speeds of up to 80 miles an hour were obtained on dry surfaces and 60 miles an hour on snow-covered surfaces without loss of control. In terms of the perceived victims of road collisions, there was no mention found in the RRL's literature of how automatically guided cars would cope when faced with pedestrians. This is particularly significant given the emphasis that is given to the way that artificially intelligent vehicles perceive pedestrians and other road users in 21st century vehicle automation. Perhaps the assumption was that road users would be segregated along earlier lines of thought, with pedestrians being kept strictly separated from vehicles in an ideal world. In this approach to road design, driverless cars would never come into contact with pedestrians. It may be too simplistic to say that pedestrians were not a concern of the development to the developers of automatically controlled vehicles in the 1960s, but they certainly did not feature in the trials of the DS19, nor in the associated literature from the early 1970s. This reflects the wider planning trend of the 1960s, which focused on designing roads for cars, with pedestrians segregated to other well-defined precincts, underpasses, and crossings. Road design was seen as something that could be changed if vehicle automation became widespread, as can be seen in Cars for Cities, with the suggestion that roads could be made smaller to maximise road capacity in congested areas. This idea was about easing congestion, which linked into the road safety problem. Vehicle design, in terms of the safety features of the car itself, automatic controls, remained a peripheral factor within the concept of vehicle automation. What was most significant in the development of driverless car technology was the idea of accident prevention. The line of thought was that accidents would not happen if the unpredictable factor of driver behaviour was removed and replaced with technology that would not make those human mistakes. With the elimination of this element of chance, coupled with free-flowing traffic and less congestion, accidents could be prevented. Vehicle automation was therefore investigated by the RRL as one possible solution to the road safety problem in 1960s Britain. The DS19 driverless car exemplifies vehicle automation as a new and emerging idea around road safety and road capacity in the 1960s. Focusing on the car as a historical resource in its own right has been invaluable for understanding driverless car technology and research during this period. RRL reports and publications by RRL staff have aided research into the mechanics of the car and how it physically worked, as well as the ideas behind the driverless car and why it was being developed at this time. But aside from these documents, the literature on driverless car research in 1960s Britain is sparse. Using the car as a historical object has therefore been central to gaining an understanding of developments in this area. It acts as more than just an illustration of information available elsewhere. Reading the car as a historical source throughout this paper has highlighted areas which would not otherwise have been apparent from using purely documentary sources. These include the numerous dials, switches, connectors and cables observed within the car and beneath the bonnet, details of the control box on the rear seat, and the significance of the use of the space under the bonnet where the spare wheel is found on an unmodified DS19. Observing the RRL's DS19 and other examples of DS19s has shown exactly what the RRL added or modified on their car and what this meant for the running of the car in a driverless mode. The car as a historical source has revealed much about the technology involved in this early example of vehicle automation. But what it cannot tell us so much about are the reasons why driverless cars were being researched at this time, what contemporary thought was on the subject, and where this fitted in with wider approaches to road planning and design. This information has come from the external sources, which have been read alongside the object to illuminate what driverless research was aiming to achieve, such as the Ministry of Transport's publication Cars for Cities. These documents illustrate a wider thinking of the period, in which the car reigned supreme and was prioritised over other forms of transport and categories of road user. They show that the car as a mode of transport received urban congestion and safety, which mass motorisation had inflicted on the country. The RRL and the Ministry of Transport predicted that vehicle automation would reduce accidents by removing the element of human error, while also increasing road capacity by enabling cars to travel closer together. The 1960s driverless car was, in theory at least, one solution to these problems caused by the car. Now, before we come to the end of the talk, there is a video from YouTube of the driverless car in action on the RRL's test track at Crowthorne, which hopefully I'll be sharing with you in a moment. Or not. Well, that didn't work quite as planned, but I can try it once more and then we may just need to move on. Let's see. For some reason, there we go. I think it's going to do it now. Sorry, it's slight technical problems, but we'll see if it's, I think you'll get it now. There you go. So thank you for listening.
Thank you very much, Georgina. That was really excellent and interesting. Thank you.